All right, in this video, I'm going to introduce you to a concept called representations of motion, and we're going to talk a little bit more about scalars and vectors. I know when I teach math, the idea of multiple representations is really important to me. Actually, it's not just important to me. I think at Glebe, a lot of teachers find it important. What we mean by that is that we can have things like tables of values, and of course, we can take that table of values and make a graph out of it. And that's an example of two things that are just shown in different ways. A table of values and a graph, they contain the same information. We can also find equations of lines, and we can describe lines in words. They're all the different ways of expressing the same thing. And what we want to be able to do both in math class, and I'm going to introduce you to an equivalent physics concept, is jump between these representations fluidly and confidently. And we're going to look specifically at some representations that we've already been introduced to fairly recently, but that's the nature of these fast-moving pandemic courses. So we've seen in this course these little dot diagrams. Now, we haven't seen them much, but this was introduced to you on the first couple of days of school. The idea being that every dot is placed or dropped after an equal interval of time. In class, I think I did a dropping chalk example. If I drop a piece of chalk every second and that piece of chalk falls and sits and doesn't roll, just by looking at the pattern of the chalk, you can tell a lot about how fast I'm going, and you can also tell what direction I'm going if you know sort of the start of my chalk drops. And we've also today been introduced to velocity time graphs, and we've previously seen position time graphs. We've also seen vectors, so drawing little arrows and describing these things in words. So they're all representations we've seen a little bit before, but we want to be able to jump between them and generate other representations given any representation. So I'm going to do a couple of examples here for you, and you're going to have some follow-up work to do of a similar nature. So here we have a motion diagram. When you get these motion diagrams, remember that the events that take place are shown with numbers. So 1, 2 means that at this specific point, event 1 happened and event 2 happened. And this is where event 3 happened and event 4. If we see two events taking place at the exact same dot, it means that there was multiple dots, multiple pieces of chalk dropped in that exact location, or multiple dots placed right at that location. And so what that would mean is that in this first interval, so interval 1 to 2, the person or the object is not moving. They are at rest. Now from event 2 to event 3, we can see there's some spaces in the dots. And so as we're going to do with most of our activities, we are going to take moving to the right or moving east as our positive direction. In this case, event 2 takes place here and event 3 takes place here, which means we're moving to the left, moving to the west, moving in a negative direction. All of those three things are synonymous in this case. And so we are moving, I want to be consistent with how I phrase this. We are moving in the negative direction. And are we moving quickly or slowly? The space between the dots, because we've got big spaces between the dots, it means every dot that takes place, we're moving further. So we're moving fairly quickly. And between event 3 and event 4, so now when we see dots down suddenly jump below the arrow, we're suggesting or implying there's a change of direction. And so they walk to the left or the negative direction, and then they turn around between event 3 and event 4 and move to the right or the positive direction. And in this case, they are moving slowly. We don't know exactly how slowly, but more slowly than before. And so moving in positive direction slowly. We might also add, oops, steady speed. Same thing up here. And that's because the spacing between the dots is constant. All right, position time graphs, we've got some experience with this. The start of our journey is quite far from our point of reference. And so on our position time graph, we're going to start fairly far away. I don't know exactly how far, don't take out a ruler. We're going to move quite quickly in the negative direction until we reach event 3. So something like that. So here's our event 1 and our event 2. Here's our event 3. When we get to, oh, you know what? I messed up. Bad job by you, Mr. John. I did not do that on purpose. I do make mistakes on purpose sometimes, but that's not an example. Events 1 and event 2 take place at the same time. We're not moving. Okay, read your description, Mr. John. We're not moving. Okay, so we're going to spend a bit of time not moving. Our position time graph stays horizontal. And then we move quite quickly in the negative direction. Something like that. There's event 3. And then we move slowly in the positive direction. Of course, that slowly means we're not going to have as steep a line. And that would be the end of our journey. Okay. Velocity graph, we've seen how walking at steady speeds on a position time graph corresponds to horizontal lines on a velocity time graph. And so, first of all, we are starting and we're not moving for a little while, even though our position time graph is up here high on the x-axis because we're fairly far away, we're not moving. And so our velocity time graph is going to look something like that, just a horizontal line. There's event 1, event 2. So in between event 1 and event 2, we're not moving, our velocity is 0. After event 2, now we start walking quickly and we're walking in the negative direction. So we're going to see a line that looks like that. Okay, so this suggests a constant velocity, and because our horizontal line is below the x-axis, we're walking in a negative direction. Our velocity is negative. And then at event 3 to event 4, now we are walking away. Away is the positive direction, and we're doing it slowly. So we're going to have a line, a horizontal line above the x-axis, or above the v-axis, I suppose, in this case, something like that. And there is event 4, and we're done. Velocity vectors. Velocity vector from 1 to 2, we're not moving. We can represent that just with a dot. That tells us not moving. Between event 2 and event 3, we're moving quite quickly in the negative direction. So we're going to have a velocity vector that is fairly long, and it's pointing to the left, because the left is our negative direction. And between events 3 and events 4, we're walking to the right, we're walking in the positive direction, and we're walking slowly. So we're going to have a vector arrow that is shorter and pointing to the right. Okay, so all of these representations go hand in hand. It's they really contain much of the same information. So there's your first example. Let me just check my time here. Good. Here's a second example. Now in this case, we are given a velocity time graph, and we need to generate our other representations. You don't always have to do the description first. For example, I think I can get my velocity vectors fairly quickly from my velocity graph. So in between event 1 and event 2, so you can, I didn't draw them in, but you can assume these, the end of our first journey and the start of our second journey happen simultaneously. So between event 1 and event 2, we have a horizontal line, so walking at a constant speed. It's above the axis, So that tells me we're moving in a positive direction, and it's quite far from the axis. Look at that distance here, okay? And the further it is from the axis, the faster we're going, so our velocity vector would look something like that, okay? And again, this is our positive direction. Between 2 and 3, our horizontal velocity line is below the axis, so that's telling us we're moving in a negative direction. Negative direction means to the left. And you'll notice I've drawn a shorter vector arrow because my horizontal line is not as far from the axis. And between 3 and 4, my velocity time graph is a horizontal line right on the axis. It means I'm not moving. My descriptions. Between 1 and 2, what did we say? We're moving, so walking quickly away. I'll add positive direction, and we're doing it at a steady speed. Between 2 and 3, our vector arrow is to the left, so we are moving 2 to 3. We're going to the left, so we're going towards, walking towards. We're walking slowly, and again, it's a steady speed. Yes, later on, we will be seeing not steady speeds. And between events 3 and events 4, we are at rest, or not moving, whichever you prefer. Position graph. We start by walking quickly away. We don't know exactly where we start. Now, we explored this already. Our velocity graph doesn't tell us exactly how far we were to start. It doesn't tell us at all how far we were to start. And so you can choose to start really anywhere along your position axis here. Seeing as we're walking away, it means we're going to have an upward sloping line. I'm going to assume that we're starting quite close. And we are walking at a steady speed, and our position is increasing, or the distance we are from the sensor is increasing between events 1 and events 2. We are now quickly turning around and walking slowly towards, and then between events 3 and events 4, we are not moving, so we'll have a horizontal line. Motion diagram. We are going to start now drawing motion diagrams on Jamboard here, and you're going to be using Jamboard to some extent. It can be a pain. If you want to do little ticks instead of dots, you go ahead and do that. Let me show you what I mean by that. We're going to start our journey. We started our journey fairly close to the sensor, to our point of reference. And so I'm going to start my journey there. So there's event 1. We're walking quite quickly away. So I'm going to see something like this. This is where you can feel free to do these with ticks instead of dots. The dots are a pain to draw. I've got them fairly evenly spaced. I'm trying to make them as even as I can. And that's going to be event 2. Now I'm walking slowly towards. So I'm going to jump down below the line. It means I'm changing direction. Now I'm walking slowly. So I've got my ticks spaced more closely, and then I stop. So at event 3, I stop, and I remain at rest for a while, and so I basically just keep other ticks here, but I don't really need to draw those over and over. I just write comma 4. It means I stood still between events 3 and events 4. Okay, so that's how we do, that's how we show these different representations of motion. And you've got 4 examples to practice. I'm not going to post solutions right now, but I will be sharing those things at some point in the future. These should all be evenly spaced. The last couple ended up a little bit closer, but I'm not going to nitpick too much about that. Try to make them appear evenly spaced, and I'll give you the benefit of the doubt. We have been introduced to some symbols, some new symbols already. The vector symbol, you're going to see little triangles, and I want to spend a bit of time explaining some of these symbols because getting used to the symbols, it's like the language of physics, it's like the grammar of physics. You're going to have to get used to them, and so I'm going to make a little summary here for your benefit. So distance, we will often use the letter D, and you will often see a little triangle included in front of it. The little triangle is a Greek letter. It's the Greek letter delta. I don't know why I did that with cursive. It just happened. Delta, and it means the difference. Delta means the letter D, but we often associate it with the difference of something. D, delta, difference. So if you see this little triangle D, it means it's the change in distance. The units, it's going to be too big. Can I make, okay, meters, centimeters, feet, any of your standard distance units. If we're just talking distance, we're talking about a scalar. It means I don't know which direction I've moved in necessarily. I just know how far I have walked. And so an example would be something like, I have walked 5 meters. I don't know in which direction. I just know that I walked 5 meters. Position is now a vector. We talk about position. We want to know distance as well as direction. Again, our units are going to be the same. They're going to be meters, centimeters, feet, anything associated with a length. In this case, we are talking about a vector, hence the little arrowhead above. And you might see a position something like this. I'm 5 meters east of the origin. Which we will often write like this. Oh, can I do square brackets? Oh my goodness. I've got a Mac keyboard and I don't see my square brackets anywhere. So I'm going to handwrite it in. You'll often see square brackets for the direction of vectors. So 5 meters east. Without that square bracket in the east, it's not a vector, and it's missing information for our position. Displacement is similar, sort of distance, position, and displacement kind of go hand in hand. Now we're talking about the displacement vector. Same units. We're talking about a vector. What I mean by displacement is how far you moved, direction and distance. So you might say you walked 3 meters, and I can't do square brackets, so I'll just draw it in by hand, west. Okay, so it's a subtle difference here between position and displacement. Position, I am 5 meters east of the origin. Displacement, I walked 3 meters west. Okay, both are vectors, and there's a subtle difference between them. Time interval, delta t. Okay, so the delta means the difference. So if I started my walk after 3 seconds and ended my walk after 5 seconds, the delta t, the difference, would be 2 seconds. Our units are going to be things like seconds, minutes, hours, anything time related. This is a scalar. Walk for 10 seconds. Okay, there's no direction associated with that. Speed. Speed suggests or implies all we are asking for is how far we walked. How fast we walked. Okay, so we often use the letter V, velocity. But if we use the v without the little vector symbol, it means we're talking speed. It means we don't care what direction I moved in. You'll often see this in meters per second. We may also work in kilometers per hour or anything else, speed, miles per hour, something like that. Okay, it's a scalar. And an example of how that would be used would be something like, I walked at 3 meters per second. I have no idea which direction I went in. Velocity is a vector. Same units, meters per second, kilometers per hour. When we see the little arrowhead up top, I need to know how fast I walked. And I'm going to do, oh, there's my square brackets. Oh. North. So that's how we would write a velocity vector. And I've got a little visitor just walked by. It's Sunday afternoon for me, 3:26. Average velocity. We're going to explore this concept a little bit more in the coming days, but just to emphasize that sometimes we're going to see these little subscripts. Oh, this is not going to be very clear. Yeah, let me erase this. We're going to add these little subscripts in. VAVG stands for V average. We're talking about a vector, same units. It's a vector, and same as this. I'll explain average velocity, the difference between velocity and average velocity in the next few days, possibly tomorrow. Acceleration is the last one that you're going to see a lot. It's denoted by the letter A. It is a vector. The units on it, we're going to look at that a little bit later. So you can leave that one. You can leave the details of, the details of that. It's a vector. And when we start looking at things speeding up, I don't want to give too much away because we're going to be exploring these things. We're going to be looking at things like speeding up. Okay. And we really have only seen one important formula so far, which I think you might have seen just in this the last block when you were working on things. And it is the connection between velocity and time and distance. Personally, I always, if I'm trying to calculate velocity, if I'm trying to calculate how fast I'm going, and I often have a hard time remembering, do I do distance divided by time or time divided by distance? I like to ask myself, I'm driving on the highway at 100 kilometers per hour. Kilometers per hour, that's a distance divided by time. And so the important formula here is our velocity as a vector is equal to our distance. So distance traveled, and oops. Our distance traveled divided by the time. And again, the little deltas mean the change in distance or the change in position. So this means how far I traveled, and this is how long it took me to travel that distance. You'll often find instead of using the letter D, we use the letter X. And I know there's a lot of variables coming at you, but these are the conventions that we need to get used to. Okay, that's the only important formula I think that we've seen so far. We're going to have about 5 or 6 other ones that we're going to discover in the coming days. But for now, you can just fill that one in and leave yourself a bunch of space there for the other ones. Okay. Most important stuff of this little lesson is these representations and jumping between them, and you're going to have some time to practice those, and they will be taken up at a later point in time. So good luck with that, everybody, and that's all for now.